Good morning, everyone. My name is Fabio Valerio Massoli, and I am a postdoc at the CNR in Pisa. Today, I'll talk about our work entitled Cross-Resolution Deep Features-Based Image Search. So just as a brief introduction, we know that nowadays deep neural networks has an astonishing capability of generating highly discriminative feature representations of the given inputs. And thanks to that, they have already reached superhuman performances on some specific tasks, such as image classification. But what we have noticed in our study is that the discrimination power of this deep representation basically degrades when a low resolution or an even worse cross-resolution domains are met. And so what we have tried to do is to formalize a training procedure which empowers deep neural networks to generate resolution robust deep features. And our approach can be thought as an alternative to other techniques such as the super resolution. As I'll show you in a few slides, we tested the performance of the model that we trained with our approach on the task of the face image retrieval. Such a task can be divided in two stages. A former one, which is an offline stage where the database of known identities is constructed, and an online stage where the query image is presented to the retrieval system that extract the feature representation and evaluate its similarity with the features, with the representations contained into the database in order to retrieve the most similar ones. When talking about face recognition, usually two protocols are used to evaluate the performance of a system, namely the face verification protocol, which consists in decide whether two images belong to the same identity or not, and the face identification protocol, in which the system has to decide whether the query's identity is contained into the gallery. And so we basically started from the face identification protocol, and we formalized the face image retrieval task. So the first ingredient of our experimental setup is, of course, the definition of the task. And in our case, it is the face classification task. Then we need a dataset to train our model, and we use the VGG phase 2 dataset since it has very nice property to train deep neural networks in the task of face classification. Then, as architecture, we choose the residual net 50 architecture equipped with the squeeze and excitation blocks that basically allow the model to recalibrate the inner representation. And then, instead of starting from scratch, we fine-tune the state-of-the-art model published by the VGG group in 2018. So as long as we train and test our models with data sets that have been acquired in controlled environments, everything works really, really well. And so, for example, here on the left, you have an example of images taken from the VGG phase 2 datasets, and you can see all the images are at very high resolution, nice and clean. While on the right, you have an image taken from a surveillance camera, and here you can see how the face appears with, the face image appears with a very low resolution. And this is the cause of serious troubles for deep neural networks. Indeed, here on the left, you have an example of a t-SNE representation of deep features extracted by, from images that belong to 20 different identities. So on the left, you can see that the model is able to distinguish all the identities among each other, while on the right, you have the very same images that we used on the left, but downsampled to a very low resolution. And so here you can see that basically the model is not able anymore to distinguish among the different identities. Typical approaches to solve, or at least to try to alleviate such a problem, are the super resolution techniques, the common space projections, and gallery downscaling. And our approach can be thought as an alternative to all these approaches. So our training procedure, so you can read this slide from top to bottom, right to left. So in the top right corner, you have an example of VGG phase 2 phase images to which we applied our procedure, the technique that we are proposing in this in our study. And then you have the processed images, which are then fed to the neural network to train. Our training strategy can be divided into two parts that both consist of one random extraction. A former one is used to decide if to downsample or not the input image. And a second one is used to decide at which resolution we want to downsample the image. To evaluate the performance of our models, we use three different metrics: the precision at K, the recall at K, and the mean average precision. So here you see the results that we obtained on the VGG phase 2 test set. So basically, we construct our database using images from the VGG phase 2 test set, so images that we didn't use while training the model. And before to construct the gallery, actually, we randomly selected 10 images for each identity from the test set and used them as query. So as you can see in the leftmost plot, and then each plot corresponds to a different query resolution. So from left to right, you have queries at resolution of 8, 16, and 24 pixels respectively. So as you can see, the blue curve represents the performance, the precision at K as function of K, of the original state-of-the-art model, while all the other colors represent different models that we trained with our procedure. In the legend, the no FT model is the state-of-the-art original model, while the FT at 0 point some number represent our fine-tuned model. Specifically, what we report in the legend is the probability that we use to decide if downsample or not an image. So for example, FT at 0.7 means that in 70% of the cases, we downsample an image. So this approach has the advantage that while training, the model is fed with very different resolution images. In this slide, you have results still on the VGG phase 2 dataset, but in this case, we evaluated the recall at K. Also in this case, you can see how our technique is able to improve basically up to 1 order of magnitude upon the performance of the original model. Moreover, you can notice that as the resolution becomes higher, basically the gap between the original model and our models is less pronounced, and this is somehow expected since at high resolution the original model recovers its original state-of-the-art performance. So finally, we have the mean average precision results on the VGG phase 2 datasets and also on the tiny phase dataset. So regarding the VGG phase 2 dataset, we have the mean average precision as function of the query resolution, and we reported in bold the performance of the best model. As you can see, from 32 pixels down to 8 pixels, our models performs much better than the state-of-the-art model, while for higher resolution, we have a tiny drop in terms of performance. So we gain up to 1 order of magnitude at the low resolution, and we lose at most 1% in performance at high resolutions. Concerning the tiny phase dataset, this is a very interesting dataset since natively it contains surveillance quality images, so low resolution phase images. So in this case, we don't need to downsample the original images, and also in this case, we can see that our model performs better than the original state-of-the-art model. So to conclude, we have seen that deep models generate highly discriminative features, but the discrimination power of such representation dramatically degrades when the low and the cross resolution domains are met. To try to alleviate such an issue, we proposed a training procedure that can empower a neural network to generate resolution robust deep features. And our approach can be thought as an alternative to other techniques, such as, for example, super resolution ones. Of course, this problem is still an open problem that needs to be studied even further, maybe we'll do in very next future. So I thank you for your attention. I hope you enjoyed my presentation, and I'll see you at the conference.